A truly useful quantum computer, it's always felt like something straight out of sci-fi, right? Always just around the corner, but never quite here. Well, a huge breakthrough from Google might have just changed all that. So today, we are going to break down exactly how they cracked a critical piece of the puzzle on the path to making quantum computing a real thing. It really all boils down to a question that honestly affects every single one of us. I mean, think about it. We have all this incredible computing power, right? So, why is it still so hard to design new life saving medicines or, say, super efficient batteries from the ground up? Well, the answer is kind of simple and kind of mind blowing. Our best computers just don't speak the language of the universe. They're trying to describe everything with just two words: zero and one. And that very limitation, well, that's what creates what we can call the classical computing wall. It's this fundamental barrier, this roadblock, that's been stopping us from tackling some of the biggest problems humanity is facing. Okay, so here's the fundamental difference, right? Your phone, a massive supercomputer, they all have to take shortcuts. They approximate. So let's say you're trying to design a new material to suck CO2 right out of the air. You can't really do it perfectly because your computer has to keep, well, rounding up the numbers for where an electron is. It's not exact. But here's the thing. Nature itself, down at the tiniest level, plays by these incredibly weird and wonderful rules of quantum mechanics. You've got things like superposition, where a particle can literally be in multiple places at once, and entanglement, where two particles are linked no matter how far apart they are. It's wild stuff. And a quantum computer, it's built from the ground up to use those exact rules. It speaks nature's language, which means it can simulate it with incredible precision. Okay, but here's the catch. Speaking the language of the universe, it's ridiculously hard. These quantum states are unbelievably fragile. And for years, pretty much everyone in this field, we're talking Google, IBM, all the startups, they've all been fighting one massive, stubborn enemy. And that villain, the big bad of our story, is simply errors. The basic building blocks of a quantum computer are called qubits, and while they're incredibly powerful, they are also just so fragile. I love this analogy. Think of a qubit like a delicate soap bubble that's holding a really complex thought. The tiniest little thing, a stray bit of heat, a random cosmic ray from space can just pop it. And when it pops, the whole calculation is ruined, instantly. And it's not just a small problem. As Google CEO Sundar Pichai points out, the problem actually gets worse the bigger you try to build your computer. In the past, adding more qubits just meant adding more ways for things to go wrong, more ways for errors to sneak in, and just wreck the whole computation. This scaling problem, man, it's been the great wall of the quantum world for decades. It's been the one thing that made a big, truly useful quantum machine feel almost impossible. So how do you even begin to fight that? Well, the strategy is called quantum error correction. And the basic idea is, it's just brilliant. Instead of putting all your trust in one of those fragile little physical qubits, you spread the information out across a whole team of them. This team then works together, acting like a single, super robust logical qubit. And this team can actually spot and fix errors as they pop up. It's a fantastic idea in theory, and for a long time, just proving this could actually work at a large scale, that's been the holy grail of quantum engineering. Which brings us right to the heart of the story, the breakthrough. Because this is the moment where Google's team didn't just take another small step, they took a massive, verifiable leap. So here it is. The big moment happened when they ran a brand new algorithm, something called quantum echoes, on their latest quantum processor, the Willow chip. And this wasn't just some abstract test, This was a real-deal demonstration, a calculation that actually simulates a physical process in nature. And the result? Get ready for this. A speed-up of 13,000 times. No, that is not a typo. The Willow chip ran this complex physics simulation 13,000 times faster than Frontier, which, by the way, is the most powerful classical supercomputer on Earth. Let's really put that number into perspective, because it's kind of hard to wrap your head around. That same simulation, it took Google's Willow chip just a little over 2 hours. To do the exact same thing, the Frontier supercomputer would need an estimated 3.2 years. Hours versus years. I mean, that's not just an improvement, that's a whole new ballgame. Okay, so the really crucial word here is verifiable. This wasn't some one-time lucky shot, a fluke. Verifiable quantum advantage means this is a result you can get again and again. It's reliable. And that signals a massive shift. We're moving past these impressive but kind of one-off stunts and into the realm of a real engineerable capability, a tool that scientists can actually trust and use. So the big question is, how in the world did they pull this off? Well, it wasn't just one magic bullet. It was this perfect combination, a perfect marriage, really, of a state-of-the-art chip that has mind-blowing accuracy and a super clever algorithm that was designed specifically to take advantage of all that power. First up, let's talk about the engine, the Willow chip. The numbers here are just staggering. So fidelity is just a fancy word for accuracy. And in the quantum world, anything less than near perfect can just completely kill your calculation. To get to 99.97% accuracy on single qubit operations and almost 99.9% on the super important entangling operations, that is just insane. It's like building a normal computer chip where pretty much every single transistor works perfectly every single time. It's that level of precision at this scale that suddenly makes the impossible seem, well, possible. All right, now for the software side of things, the algorithm. And this is where it gets really cool. This quantum echoes idea is just ingenious. Here's how it works in a nutshell. You let a quantum system evolve forward in time, then you give it this tiny little nudge. They call it a butterfly perturbation, and then you run the whole thing backward in time. Now, because this is quantum, the forward and backward paths interfere with each other, and that creates this measurable echo. And that echo is incredibly sensitive to everything that happened inside the system. Seriously, it's like shouting into a huge canyon and then being able to analyze the echo to map out the location of every single rock and pebble. It's that precise. Okay, that's all really cool, but what can you actually do with a technique like this? Well, the first really tangible application, the first proof of concept, is a new tool for chemists that they're calling a longer molecular ruler. So what this does is it massively enhances a standard scientific tool called NMR spectroscopy. The easiest way to think about NMR is like an MRI, but for single molecules. It lets you map out their structure. Now, the big problem with regular NMR is that its signal gets really weak over long distances, so you can only see how atoms that are right next to each other are connected. But by using quantum echoes to simulate how that signal travels through the molecule, scientists can now see the connections between atoms that are much, much farther apart. This could be an absolute game changer for designing new drugs and creating new materials. And you have to understand, this achievement didn't just happen out of the blue. It's not some random fluke. It is a critical milestone on a very deliberate, very carefully planned long-term roadmap.
Hartmut Neven, who is a real pioneer in this space and leads Google's quantum AI lab, he basically puts it like this. Now that we see what this quantum echoes algorithm can do, we get why they're so optimistic. They really think we're going to see real-world applications from this stuff within just 5 years. I mean, that is an incredibly bold prediction, but after this, it actually sounds plausible.
And when you look at their track record, you can really see the strategy playing out. Back in 2019, they showed they could do a calculation that no classical computer could handle. Then in 2023, they proved that a basic error correction prototype could actually work. And now, with this latest step, they've hit verifiable advantage. You can see how each milestone builds right on top of the last one. And the next huge goal, building a truly stable, long-lived logical qubit. That's the real building block you need for a fully fault-tolerant quantum computer. So, if there's one thing to take away from all this, it's this. Quantum computing is finally turning a corner. It's moving out of the realm of theoretical physics and into the world of practical engineering. We are now on a clear path, an actual roadmap to solving problems that have, until now, been completely impossible for any machine humanity has ever built. And that leaves us with a pretty profound question, doesn't it? As this incredible new power comes online and becomes a tool we can actually use, we really have to start asking ourselves, once we can simulate nature perfectly, once we can unlock its deepest secrets, what's the very first problem we should solve?